Hello, I hope you're all well. My name is Brett Martin. I'm a first year PhD student at the University of Derby. My project focuses on the paleontology of the Maltese Islands and the secrets it holds. Dominantly, how the geology of the islands can be compared to current climate events and the effects on our marine ecosystems that could be predicted. The project follows on from my independent study, and so I'm able to describe some findings to you. So, why? Well, to appreciate this project's importance, we must firstly understand its goal. That is to extrapolate the effects of modern climate change on the planet's marine ecosystems. We know about the effects of rising sea surface temperature and ocean acidification, both results of global warming. Climate change is also changing the usual circulation of our oceans. The effects on corals and anthozoa around the world is known, which is enough food for thought. But the severity of the effects of these changes on bivalves, echinoderms, and bryozoa, for example, are not so well understood because they are less researched. The Maltese Archipelago presents the perfect study area in order to investigate the effects of paleoclimate change. This is thanks to its incredible geology made up of mainly biomimetic limestones from the Upper Oligocene to the Upper Miocene. The stratigraphy begins with the lower coralline limestone. Above this is the lower globigerine limestone, a biomicrite rich in bivalves, heart urchins, and globigerine foraminifera. You'd be hard-pressed to find any notable fossils in the white marlin middle globigerine limestone or the upper globigerina, a yellow biomicrite. The next two units, the blue clay and green sign formations, are not continuous units and are rarely seen. The uppermost, Upper Caroline limestone, though, is a stark contrast to all others, with daisy-cladation algae, crustose algae, large agglutinated textularia present, as well as coral communities visible within the rock. As with my independent study, data collection is as simple as a random sampling method, as seen in the right image, and a tally of all fossils found. What we find is that the abundance, species richness, and diversity of the paleo ecosystem changes, as well as the existence and proportions of certain species and phyla. The kite diagram shows the changes in abundance of a few particular species of bivalve and echinoid. We also find that the physical and chemical components of the ecosystem changes, too, with the sea level, sea surface temperature, oxygen concentration, circulation, and acidification all fluctuating. Some environmental factors, especially depth and circulation, can be attained from the suite of microfossils at any one point in the stratigraphy. As one example, the middle globigerina limestone of mid-Miocene age is sparse with fossils and contains oncoids. The particular oncoids of this unit indicate a very deep ocean, a contrast to the lower coralline and upper coralline limestones of less than 100 metres deep, proven by the presence of photosynthesizing algae. Because we see clear points where the paleo ecosystem is under significant stress and points where stress is low, we can correlate these instances with major climatic events such as the MI1 cooling event, mid-Miocene climatic optimum, and mid-Miocene climatic transition. The most resolute way to do this is to do something that's never been done before, and that is to attempt the uranium-lead radioisotope dating from LA-ICP-MS of the Maltese limestones, taken from points in the stratigraphy that the paleontology shows significance. Accurately dating major paleontological changes will allow climate events to be correlated with it, cause and effect. In the graph, delta oxygen 18 levels, the black line, directly mimics global temperature due to the fluctuating glaciation. Folmy et al. 2008 dated the phosphorite beds of the islands, of which there are two major ones, at approximately 22 million years ago and 14 million years ago. These are a good place to start considering their association with acidification and hypoxia, proven by the presence of high concentrations of the mineral glauconite. Their ages are marked on the graph as red arrows, showing correlation with increased temperatures and their standout clastic nature seen in the field on the right, very easy to spot. So overall, by correlating major changes in paleoclimate with paleontological changes, we can begin to infer similar effects on our modern marine ecosystems, which may include high stress and reduction in species richness and diversity. Understanding the potential future for this planet's marine fauna today will help us adapt our conservation efforts more comprehensively, saving millions of species across the globe.